Welcome to qnawire.
Hi, so for this question, we're going to start with a 35 milliliter solution of 0.2500 molar HF. We are given that the value for Ka, or the pKa for this acid, is going to be equal to 3.17. So this value is not provided in the problem, but you can find it easily in a table. And we want to perform the titration of this with a 0.1998 molar solution of NaOH. So the first question is, what is the pH before the titrant is added? In order to do this, we can directly draw up our ice table. We have HF plus water is going to generate H3O plus F minus. The initial concentration, we're going to label this as C0. The amount of change is going to be minus X, with begin with 0 and 0. This is X, this is plus X in both of them. So we end up having C0 minus X, X, and X. The Ka for this reaction is the concentration of H3O plus times the concentration of H minus divided by the concentration of HF that we have in solution. Remember that water doesn't matter in the ice table nor in the equilibrium constant because it's a pure substance. It doesn't enter into those values. So Ka is nothing but x squared divided by C0 minus x. But we know that Ka is going to be equal 10 to the minus pKa, so 10 to the minus 3.17. So we know that x is going to be a small value. So what we can do is approximate C0 minus x. It is going to be approximately C0. And then this is going to be true if x is lower or equal than the 5% of my initial concentration that we have. With that taken into account, the value for x is going to be a square root of Ka times C0. Replacing the values that we have, 10 to the minus 3.17 times 0.25, and it's going to give us 0.013. Or without rounding up, this is going to be 0.125. Sorry, I meant that by solving the full quadratic expression, the result would be, so this is the result by our approximation. If we solve this directly for x, the value for x that we find is 0.0126. Okay, so what is this x? That x is going to be the concentration of H2O plus that we have. So recall that this is concentration of H3O plus in both cases. So if we use our approximation, we find a pH of 1.88. And without any approximation and solving the full quadratic expression, we get a result of 1.8975. So both of those results are valid. You just need to say what is the procedure that you follow. So in this case, since the value is slightly larger than 5% of the value for C0, I would stick with the solution of the full quadratic expression. So next up we have what is the pH at 0.5 milliliters before the equivalence point, and what is pH 0.5 milliliters after the equivalence point. And also we want to know how many milliliters of titrant are required to reach the equivalence point. So since we have an initial amount of HA in moles, it is going to be 35 times 10 to the minus 3 liters. This is the volume of the solution that we have, times 0.25 molar. This is going to be 8.75 times 10 to the minus 3. And since we want to find the equivalence point, well, the amount of OH that we need to add needs to be equal to the amount of HA. And that amount is equal to volume times the concentration. And the concentration for NaOH, from here we get that the volume, it is going to be equal to the amount of mole that we require. This is a 1-to-1 reaction, divided by the concentration of my titrant, that is 0.1998 molar. So the volume required is 43.79 milliliters. Of course, this is 0.04379. After liters, convert this to milliliters, and we get the final result of the volume required. So now, what is the pH at 0.5 milliliters before the equivalence point? Well, what we can do is, first of all, we're going to round this up as for 3.8 milliliters. So in part C, 0.5 before means that we have added 43.3 milliliters of NaOH. The amount of mole of NaOH, then it is going to be concentration times volume, 0.1998 times 43.3 times 10 to the minus 3. Times 0.1998 molar. This is in liters. This is going to give us 8.65134 times 10 to the minus 3, or approximately 8.65 times 10 to the minus 3 mole. Okay, so now we can proceed with our ice table. Plus OH minus, producing water plus A minus. We initially are going to have 8.75 times 10 to the minus 3. We are going to add 8.65 times 10 to the minus 3. The amount of change is given by the limiting reagent, which is the OH minus. Zero. This result with plus. That means that at equilibrium we're going to get 1 times 10 to the minus 4 of HA, something close to 0 of OH minus, and 8.65 times 10 to the minus 3 of A minus. We have an acid and base pair, so we can calculate the pH, and all of this is in mole. We can calculate the pH directly using the Henderson-Hasselbalch equation. So we said that the pKa for this acid was 3.17. Recall that pH is equal to pKa plus logarithm of the concentration of A minus divided by concentration of HA. Since this is a quotient of concentrations, you can go directly and put the values for moles because the total volume is going to cancel out. So pH is going to be equal to 3.17 plus logarithm of 8.65 times 10 to the minus 3 mole divided by 1 times 10 to the minus 4 mole. In this case, we should put the total volume, but as I mentioned, it doesn't matter because both of them are going to cancel out in our equation. So we can live without them and simply do this operation as is. So with this, the result for the pH at 5 milliliters before the equivalence point is going to be 5.107. And now we want to know what is going to be the pH at 0.5 milliliters after the equivalence point. So after the equivalence point, what is going to happen is that the pH it is going to be given by the excess of OH minus that we have added. So in 0.5 milliliters, so this is part C, of extra NaOH, the amount of moles that we are going to have are 0.5 times 10 to the minus 3 times my concentration that was 0.1998 molar. So the amount of mole extra of NaOH or of OH minus is going to be 9.99 times 10 to the minus 5. Now, what is the volume at this point? The total volume, it is going to be, to reach the equivalence point, we said that we require 43.8, right? So 0.5 after, it is going to be 44.3. milliliters that we have added of NaOH plus the initial volume of my solution, which is 35 milliliters. This is going to give us a 79.3 milliliter, which is the same as 79.3 times 10 to the minus 3 liters. This implies a concentration of OH minus equal to 9.99 times 10 to the minus 5 divided by 79.3 times 10 to the minus 3. And the result is 1.25977 times 10 to the minus 3 molar concentration. So now with this concentration, I can calculate the pOH. Remember, this is minus logarithm of OH. This value is going to be equal to 2.9, and the pH is 14 minus pOH. So the pH for the solution, it is going to be 11.1 after the equivalence point.